All right, g'day. What are we doing? Uh, so welcome to the eighth video in this series. Um, there's something that I really like about this series, and that is the enormous amount of mistakes and issues that I've encountered. It has been pretty spectacular. I like that nothing's been scripted, obviously. I just record these off the bat, and it really has felt like just about every day I've encountered a new problem. Let me explain to you today's problem. Um, so when we have when we have a two-tailed test, what's happening is the decision trees are being constructed. Each node has a certain number of features that we're testing. And in a two-tailed test, let's say you have the gender variable, you have masculinity and femininity. What's happening is at each of those nodes, certain features are kind of pulling the classification towards one way or the other, right? Because it's a two-tailed test. The middle is a neutral point, and then we have masculine and we have feminine, right? And each of these features is pulling the sample towards a classification. Now, the feature importance reports which, like, kind of the strength of that pull. How strong is the pull towards classification? But because the XGBoost algorithm is what we call a black box model, which means that it is really difficult to kind of look inside it and see how it's making decisions, we don't know which direction. I call this directionality. I'm sure that there is already a word that's different to that. I don't know it, but I call it directionality. What is the directionality of a feature? In this case, does a, does a certain phoneme contribute to a male classification or a female classification? So I currently have a study that is under review, which is looking at gender. And the way that we looked at classification, directionality, sorry, for gender was that we just looked at the distribution of phonemes to a category. Now, with gender, it doesn't matter. With gender, that we saw in video 2 or video 3, we ran the linear regression model, and it showed that there's no significant correlation between gender and length. So there is no, it was fine to use distribution. However, we also saw in that video that just about every other psycholinguistic, every other dependent variable had a significant correlation with length. Now, we tried to fix that. We tried to reduce the strength of the effective length in these models. And we did that with this bit of code here, which it counts the number of times a phoneme occurs in a sample, or a word in this case, and then it divides that by the total number of phonemes in that word, so that the total length of the word. And what we ended up with was those fractions. And in the last video, we talked about how those fractions interact with the gradient descent algorithm and all the problems that causes. Well, we fix those problems. However, we're still dealing with this issue, because if you think about it, the issue isn't really even if you divide it by length, you're still going to have this issue of length. Because if you have at one of those nodes, let's say you have a feature, and almost all of those features, or all of those features, have a null value of 0, have a null value except for one. And it doesn't matter if that value is a 1 or if it's a 0.00001, it's going to have the same effect. That's the only useful information at that node. So it's going to go by that information. So it doesn't matter that we divided it by the total length. That matters for feature importance. It does matter. It does matter, but it doesn't undo the entire, it doesn't fix the problem, right? The entire problem hasn't been fixed. So I discovered this problem by looking at the distribution. There's a code. I'm going to leave it in the script just for your if you're going to use this code for something that's not affected by length, I'm going to leave it in the code there for you, so it will be available. Let me just show you where it is. It's under phoneme distribution. This outputs a CSV file. It actually outputs 10 CSV files. However, at the end, it outputs a CSV file with the combined phoneme counts. That looks like this. And then I wrote a simple if clause, which basically said, if this number is bigger than this number, then return a value of 0 or return a value of 1. So now we know that AA for the arousal has a greater distribution for the 0 value. However, I know that this I know that this is a problem. I know that it's a problem, and I know that it's a problem because of this information here. Up the top here, these are the accuracies for the models and the standard deviation for the k-fold splits. And this is size. Now, probably size, the relationship between size and sound symbolism, that's probably the most studied relationship in sound symbolism, right? And the most studied relationship is, and the most studied language in terms of that relationship is American English. So we know what this model should look like. So the reason why I understand that distribution is problematic here is this here. Right, we have our high front vowels I and E, and they're both showing that they have a higher distribution to the large category than the small category. Well, that can't be. It's we know that high front vowels in most of or all of, I'm not entirely sure. I think that there's one study that I read where it wasn't the case, but in most of or all of, except for one, of the world's languages, the high front vowels are associated with smallness, not largeness. And certainly in American English, high front vowels are associated with smallness, not largeness. So, problem, right? Alarm bells. So how do we fix it? There is a package called PDP. PDP stands for partial. Oh, how have I forgotten this? Sorry, I am having a brain. Maybe plot, partial dependency plot, partial dependence plot, partial dependence plot. Okay, PDP stands for partial dependence plot. What it's going to do is it's going to show us how the relationship between the directionality, how a phoneme is contributing to classification. How does it do that? Good question. Let's talk about how I've set this up, because I've had to modify the data. When it was working on the fractions, right? Like how I modified it to make the model to consider to try and reduce the effective length. Those fractions were messing with my plots, because what we're going to be doing is we're going to be eyeballing plots to see if there's a positive or a negative correlation between the number of times that a sound occurs in a word and its classification. So what we've done is we have reloaded the original data set, and then I've gone back up to code lines 36 through to 188, and I've rerun those median splits. I did try this by running them as a regression model. That was taking too long. I got I'm not sure what's happening inside, but I ran it for a pretty long time. I thought what should be enough time, and it was just taking too long. So I stopped. I'll try and run it overnight at some point, just to see if it does work. But yeah, it was just too time consuming. So I reran the median split. So we're dealing with categorical dependent variables. These lines of code build a pretty simple XGBoost model without like using the default hyperparameters inside the model. However, what it's doing is it's constructing the model on the entirety of the data set. This is not a k-fold split. This is every single sample in that data set. And the reason we're doing that is because we can use the maximum amount of information. We're not feeding test data into this model. We can use the maximum amount of information that's available to us, and that's all of it. Remember, though, that that's after the subset split code, and inside that subset split code is the code that randomly removes samples in order to make sure that the two categories have an even distribution, because we know that distribution skew has an effect on these models. All right, so we train the XGBoost model. Then what we do is we run this code. It's actually this command in the PDP package, which is doing the job for us, the partial command. It's going to give us a good look inside the XGBoost model and tell us what's going on. We're going to eyeball these really. So what we're looking for is a positive correlation between the sound and its classification. However, I probably should have run these before I started recording, but yeah, as I said earlier, what I like is I like the mistakes here, and I like trying to go through the problem-solving process with you. So this first plot here, which is down the bottom right-hand corner, this is the plot for L. We have the feature name. We can do the partial plot. We run that code, and it returns this plot. And what we can see here is a positive correlation between the number of times that L occurs and its classification. So what we will do here, this is the arousal data set. This is the arousal dependent variable. So what we do here is we give it a distribution of high, meaning that that phoneme is contributing to a high classification. Now we go to AH. So all I need to do is modify this, drag it down, eyeball this chart, and we see that we have a negative correlation. So that gets a distribution of low, T. These codes are already in place. They're from the earlier one that I did, which was based on the fractions. And those charts were incredibly difficult to read, to determine. Okay, so this one here, we see like a small rise at 1 and then a drop at 2. So what do we do with this information? That's a pretty good question. I'm obviously, when I write this report, I'm going to have to talk in some detail about making these classifications. I haven't decided entirely exactly how I'm going to deal with these. The thing is that, so there's a small increase if there's one of those sounds, and then a big decrease if there's more than one of those sounds. I think that this is probably a low classification, right? Like this is probably a low. However, one occurs more than other. Interesting question. I'm not going to deal with it right now. I'm just going to leave it blank, and at a later date, when I figure out, or once I've possibly spoken to someone a little bit more knowledgeable on the subject, then I will, figure out exactly how I'm going to report the distribution. A note on the PDP package. What a lovely package it is. It is by Brandon M. Greenwell. We're dealing with the most recent version. Here's the documentation. I was very happy to find this. I really like this package. Yeah. Anyway, very useful for looking inside these black box models. Anyway, that's how I got around the issue of directionality, because those high front vowels shouldn't be associated with largeness, but the distribution was showing that they were. So yeah, it's a problem, and it's something that I have done my best to fix. But obviously, for some of these charts like this T here, I'm going to probably contact possibly the author of the package and just find out what, like, their opinion on this distribution. Anyway, that's enough for today. I hope you have a great weekend, even though you're probably not watching this on Friday. I made that same mistake twice. Fantastic. All right. I'll catch you later. See ya.